On January 1st, 2021, we have a new release of module which packs a couple of really important new features. One of these is the Conductive Backsheet, and the other is the ability to define right in module extra contact resistance either to the ribbon or to the Conductive Backsheet. So let's go over these couple of new features. As we know, Conductive Backsheet can be applied to cells where both cathodes and anode connections are placed on the rear, and these can be IBC cells or metal wrap through cells. So in this example here, we're going to load an IBC cell module. So let's open up the cell library, and here's our IBC cell. So on the front side, there's no metallization, and on the other side, there's 5 cathode bus bars and 5 anode bus bars. And here we can see it's still connected in the traditional way using ribbons. This is a screen printed IBC. The design is borrowed from ISC Constant's Zebra solar cells. And here, just arbitrarily, I picked a large cell size. The dimensions are 166 by 166 millimeter, and it has 5 bus bars, just as an example. So here, when I first load in the module, it's still connected in the traditional manner using ribbons. And I can go ahead and simulate its IV characteristics. And here's its IV parameters. The maximum power is 365 watts. Fill factor is 78.76%. And if we go to its VMP, and for example, take a look at the cell front side voltage drop, we can see clearly this voltage drop in the vertical direction of each cell, meaning there is significant voltage drop along the ribbons. And this rear side voltage goes like this. So on either side, there's significant voltage drop along the ribbon direction. Now let's contrast that to the case of Conductive Backsheet. So to do that, we open Conductive Backsheet window. And here we're allowed to import a pattern that we have already defined. So this is much like in Griddler, where you can go to AutoCAD or SolidWorks, create a pattern, save it as DXF file, and then load it in. So we're already made a pattern for a 60 cell module. And if we zoom in further, it's actually disconnected sections that look like this. So I'm gonna just grab a screenshot of this and show you the interconnections. So we can imagine this entire backsheet as a conductive foil, such as aluminum, and it's made of many disconnected sections. So the first section here, this connects to the negative terminal of the entire module, and then these 5 sections here, they make the connections to the negative bus bar of the first solar cell. Then the next section of the conductive backsheet is this one. Up here, these 5 sections connect to the positive bus bars of the first cell. And down here, the second cell will be rotated 180 degrees so that the conductive backsheet red sections are connected to the negative bus bars of the second cell. And this pattern just kind of repeats. Where now this red section here of the conductive backsheet connects to the positive bus bars of the second solar cell. And then the third cell again is rotated 180 degrees with respect to the second cell. And so this red section here will connect to the negative bus bar of the third cell, and so on. And this pattern just repeats itself throughout the entire module. So much like in a traditional 60-cell solar module, the cells are strung in this zigzag manner that spans 6 columns and 10 rows. And that means in the module we'll have to lay out the cells where alternate cells are rotated 180 degrees. So let's do that through the subcircuit library. First, we need to clear the default layout. So we start from scratch. And then we pick one single cell and insert it into module. And then we're gonna insert another cell right below this one, which is 180 degrees rotated. First, we need to define the coordinates of the second cell. So the second cell, upper left corner, should be right up against our first cell. And let's make it 1 millimeter apart. and we have to rotate this second cell by 80 degrees. So let's do that. So now we have defined this second cell. So let's save this cell pair as a unit. So we go ahead and save this as a cell pair. And then again, we start with a blank canvas. And then we're gonna insert an array of these cell pairs to create our module. So the array is gonna consist of 5 rows of them by 6 columns. So here's our 60 cell module. And if we check out the connections, they should be alternating 180 degrees rotated. Next, we'll have to align the backsheet. So to do that, we show the backsheet contour, and we also show if there's any solder points on either the cathode or anode bus bar that lands inside the backsheet, is gonna show that. So right now, because there's not a lot of overlap between the two, we don't see any. So let's go back to the conductive backsheet window, and we can define offsets. And by defining the offset, we can get the alignment right. Okay, now I think I got it perfect. So we can see here this is cell number 1, and you can see that the solder point along the positive bus bar of cell 1 are contained in this section of the backsheet, and the solder points along the negative bus bars are contained in this section of the backsheet. So this is well aligned. Now let's also define the positive and negative terminals of the entire module. So to do that, we show the nodes and the coordinates of the nodes. We'll create a node right above this one. So we go to subcircuit library, create node at 1785, and 1 centimeter above 1669 would be 1679. And we designate this node 601 as negative terminal. So similarly, we go to the other side of the module. In 85, create a node right above it. So this node 602 will be our positive terminal. So that's it. Now we've connected the conductive backsheet to all the cells and also to the positive and negative terminals of the module, and now we're ready to run its IV curve. So we see in this particular case, relative to the ribbon connection scenario, we have a great improvement in fill factor, and the maximum power as a result has increased by about 12 watts. And now if we go to the MPP and simulate the cell voltages, we see that both in the cell front voltage drop as well as the rear voltage drop, most of that voltage drop is along the direction of the fingers and is no longer along the direction of the bus bar. So that means the conductive backsheet has reduced the resistive losses that had existed along the ribbons in the ribbon connection scenario. So that explains the difference in the fill factor and the power. We can also take a look at the voltage drop along the back sheets. So here they are, and we can see they are pretty minimal. The maximum voltage drop along any section of the backsheet is only about 6 millivolts, and the ohmic losses are pretty negligible. While we're at it in this example, let's also explore the second feature, which is the ability to define contact resistance at the conductive backsheet connection points or on the ribbon. So in this case, we have conductive backsheet. We can press this N button that brings us to this graphics interface where all the connection points for positive terminals of the cell are shown here. And right now, the entire picture is 0. That means all the connection points have contact resistance of 0 milliohms. So let's draw, for example, 10 ohms contact resistance at certain position. So for example, this cell may have poor contact resistance here. And now if we do the IV trace, we get slightly reduced fill factor and slightly reduced power. And now if we go to the MPP, we see that the backsheet voltage is higher around this cell. We can also see that the cell front plane, the effects due to this increased contact resistance. So this is the graphical way of introducing extra connection point resistance. We can also do this in the conductive backsheet. So in the conductive backsheet, there is a box called contact point resistance. There's also an N button, so if we press that, that gives us a map of the contact points and their resistances. So you can see these are the high contact resistance points that's been introduced by the graphics method. So if we zoom into that, we see these are the contact points and their extra contact resistance, 10 ohms. And we can also see explicitly the node numbers, the connection point numbers. So let's use this interface to explicitly define contact point resistance for the anode points to negative terminals of the cells. So let's perhaps go to another cell. Let's say this one here, and we also assign 10 ohms to, let's say, connection nodes 2616 to 2643. So now you see these connection points have 10 ohms. So this is the second way of introducing contact resistance, which is a bit more precise. So after doing this, we can again trace the IV. So we can see here the fill factor is further reduced a little bit due to this additional anode side contact point resistance. And we can again map out the voltages at MPP. So now we see not only this cell is affected, but this cell as well. And if we look at the cell rear voltage, yes, so we see that now because of the additional anode contact point resistance we introduced to this cell voltage drop is also higher than the rest. So here we've shown you in our conductive backsheet example of introducing additional ribbon or conductive backsheet contact point resistances. In this case, conductive backsheet, but you can also do this for ribbon connections. So this is a great additional tool to investigate the impact of poor solder point connections. Or nowadays, there's a lot more interest in reclaiming modules or recycling modules after they have been used a number of years in the field. So this feature may be suitable for those kind of applications and investigations as well.